Good morning to everyone. Myself, I am G. Sunitha, degree lecturer in physics from TTWRDC Kottagudam. And now today I am going to deal with thermodynamics, and which is prescribed one, that is from thermal physics for second semester physics students. So as all of we know, we are also studied about thermodynamics in the earlier classes, that is in the lower classes. And let us once recollect what are the basics of thermodynamics. And right now we are dealing with number of aspects of thermodynamics here. So let us see one by one. So first of all, when we come across the word thermodynamics, what we think of the word here is heat. That is exactly what we can say, that thermodynamics is a branch of thermal physics which deals with the transformation of heat energy into mechanical work, and which is a vice versa. And this transformation may come from mechanical work to heat energy also. And it also deals with the transformation of heat energy to other forms of energy, such we can say that electrical energy and chemical energy, light energy, etc. Generally, the study of this thermodynamics can be, which is divided broadly into two parts. The first part deals with the relationship between the different types of energy, which is based on the first law of thermodynamics here. And the second part deals with the direction in which these particular phenomena happens, and which is based on the second law of thermodynamics. And in this class, we are going to deal with all the laws of thermodynamics here, especially the zeroth law, the first law of thermodynamics, and the second law of thermodynamics. And right now, first, before uh, uh, thinking about thermodynamics, that is, we should have to know what is a system and its surroundings. So generally what we think of a system here, generally what we think of a system here is a particular definite quantity of matter which is bounded by some closed surface here. So a system may always should have a matter and which should have enclosed by some surface. For example, if you take a gas which is which is fitted in a cylinder, that is a gas contained cylinder with some movable piston, that is treated as a system here. And of course all those things which are outside this particular system, what we have considered like cylinder fitted with a piston on it, is called as surroundings. So we should know what is the difference between this system and surroundings first, because everything, that is the choice of system and surroundings is we can take it anywhere, that is it is arbitrary here, that is quite arbitrary. We can take any system and we can take this, surroundings of the system here. So when you think of the system, the systems are divided into, of course we can say depending upon number of properties here. So these systems we can say that is either a open system or a closed system. So system in which, that is in which the heat, that is both energy and matter, are exchanged with the particular system, then that is called as open system here. I should repeat, a system which can exchange both energy and matter with its surroundings, then that system is called as an open system. On the other hand, if you say the systems which can exchange energy only, not the matter, then that is called as a closed system here. So generally what we think of this open system and closed system are, they are present in our nature itself. And if you think, that is, if there exists no exchange of heat or energy between any system, matter gani, energy gani, either if there exists no other exchange of this process, then that system is called as isolated system here. So if that isolated system is present there, then we cannot justify that it is an open system or it is a closed system. We can just go for that is an isolated system. So how could we say that is a system which has some properties, that is a number of properties are there for a system, and the behavior of the system can be explained by using these properties. So what are those properties here? We should think of the properties here. So the properties may be of small scale or maybe of large scale. We can say that macroscopic properties and of course microscopic properties here. So system behavior can be described in terms of either for microscopy and of course for macroscopic properties here. So those particular variables, that is for which the system can be explained of course from macroscopic properties, then those variables have given some name. Let us see one by one here. Yes, they are called thermodynamic variables here. So what are the thermodynamic variables here is yes. Yes, thermodynamic variables are those observable macroscopic variables of the system. We are specifying that they are observable. That means we have given the examples as pressure and volume and temperature. See, we can observe the pressure change and of course the changes in the volume and of course changes in the temperature. So if particular PVT are described in the equilibrium system of the state, then they are known as state variable, thermodynamic state variables here. And these variables are also further divided as extensive variables and intensive variables. So one is if particular system size has been dependent, then that is we can take the examples of mass, volume and entropy, magnetic moment, etc. These are the variables which depend upon the size of the system here. So if you take the mass, then if you say that is a bigger one, if you take the volume and if you consider that particular entire vessel as having less volume or bigger volume, likewise these variables are depending upon the size of the system here. So that's why they are called as extensive variables. And coming to intensive variables, they do not depend upon the size, that is pressure, this is temperature and magnetic field here. And of course the extensive variables may be changed to an intensive variables, which is known as specific value here. So we should only remember the thing is these extensive variables are converted or they can be changed into intensive variables, where we can call them as specific values by dividing by suitable extensive variables such as mass and number of moles and number of molecules. So we can say that specific value we can give it as specific heat, that is heat capacity per mass. So thermodynamic variables are used to describe the state of the system, especially in terms of macroscopic variables. That's what they are called as thermodynamic variables here. So when you come across these thermodynamic variables, we can observe number of pressure changes, volume changes and temperature changes around us. Of course pressure change may you can observe whenever there exists air that is airflow, and of course you can also observe volume and temperature changes as well around us. And before describing about this, that is thermodynamic variables, if they are intensively considered, then we have to know about the thermodynamic equilibrium here. So in mechanics, what we say, the state of a body can be specified by means of few measurable quantities, which are position of center of mass, if you consider mechanics. So position of center of mass and then its velocity and acceleration, etc. So likewise in mechanics, we are also in thermodynamics, we have the state of the system, which is represented by pressure and volume, temperature, which are provided by that system, which is in equilibrium. We say representedly pressure, volume and temperature if the three parameters describing the state of the system are called which are called thermodynamic variables or thermodynamic coordinates, especially we say. And this thermodynamic system is one which is described in terms of thermodynamic variables here. So when the thermodynamic variables attain a steady value, we can say that is they are independent of time, and the system is said to be state of thermodynamic equilibrium. What we can say, thermodynamic equilibrium in terms of this thermodynamic equilibrium can be expressed into whether the system attains different types of equilibriums here. Let us see one by one what are they. If the system is said to be in thermodynamic equilibrium, if it maintains thermal equilibrium, thermal means it is related to temperature. That means if there exists equality of temperature, then the system is said to be in thermal equilibrium state. And of course in the mechanical equilibrium, that is the equality of forces here, or which can be termed as force per unit length, which is a pressure one. So if there exists equality of pressure, then that is called as mechanical equilibrium. And of course the chemical equilibrium, that is equality of chemical potential here. So a chemical potential state should be equal in the case of chemical equilibrium. If a particular system, if it maintains thermal, mechanical, chemical equilibrium with its surroundings, then it is said to be thermodynamic equilibrium system. Okay, so the system is said to be in thermodynamic equilibrium here. So how could we express the equation of state here? So if you want to express the system state, then there should be an equation here. So what is the equation of state here is the thermodynamic state, which is one which is described in terms of thermodynamic variables here. That is thermodynamic coordinates. We say pressure, volume and temperature here. So when the two variables are out of the three are fixed, and the third one is automatically fixed, then the two parameters are necessary and sufficient to specify uniquely the state of the system here. So thus what we can say, only two parameters are necessary and sufficient to specify uniquely the state of the system. So how can we define this equation of state here is that equation that is relating to the thermodynamic coordinates here, which is and expressing the complete behavior of the thermodynamic system which is in equilibrium is called as equation of state here. I repeat, an equation which is relating all the three thermodynamic coordinates and expressing the complete behavior of the thermodynamic system which is in equilibrium, then that is called as equation of state here. And how can we represent this equation of state here is, it is a function of these three thermodynamic variables. First one is pressure, volume and temperature. So how can we express this equation here is function of f of p comma v comma t, that is equals to 0, because the system is said to be in thermodynamic equilibrium state. That is, there exists the thermal equilibrium as well as along with the mechanical equilibrium, chemical equilibrium also. And of course and next what we are going to deal with, let us see, that is for the zeroth law of thermodynamics here. So how can we say the zeroth law of thermodynamics is there? If a system is there, when we come across this zeroth law of thermodynamics, we should consider three systems here. So that is, if you already we told with what is a system here, we are just considering three systems, that is A, B and C. Let us see how they are related. If A is in thermal equilibrium with the second system B, then the two systems are said to be in thermodynamic equilibrium. And if these two systems are in individual equilibrium with the third system, A, B, C, three systems are there and two systems are in thermal equilibrium with the third system separately, and that is separately means they are in thermal equilibrium with each other. That's why if you observe the figure, you can have an idea. Yes, two systems in thermal equilibrium with a third system separately or in thermal equilibrium with each other. You can observe the figure and you can see, you can check it. System A and system B both are in thermal equilibriums, and these two systems are in individually in thermal equilibrium with the third system, we say that is system C here. So what is generally to know about this, what is the aspect to know about this zeroth law of thermodynamics here is, it clearly suggests the two when two systems A and B are in thermal equilibrium, there must be a physical quantity that has the same value for both of the systems here. So this thermodynamic variable whose value is equal to two systems which are in thermal equilibrium is called as temperature T. So if A and B are separately in thermal equilibrium with C, then temperature of A is equals to temperature of C and temperature of B is equals to temperature of C. That means temperature of A is equals to temperature of B. So the systems A and B are also in thermal equilibrium with each other. So how could we express this is, if you consider a system which is which we have discussed, that is example for a system, a cylinder which is having that is having a movable piston in which some gas is there. So if we take such system as an example, if we consider the zeroth law of thermodynamics, then we should say that two systems are in thermal equilibrium with the third system separately, which are in thermal equilibrium with each other. And if you want to talk about the temperature, we should have the knowledge of heat here. So what zeroth law of thermodynamics says here? So zeroth law of the thermodynamics leads to a concept called temperature here. So what is the temperature generally? Concept of temperature. So all bodies are having temperature. So how could we know whether temperature is a property or temperature is a measurement, first of all? So let me check once. Yes, temperature. First of all, before going to deal about this heat, we should know the concept of temperature here. So all bodies in thermal equilibrium must have a common property which has the same value for them, which is the temperature. So this property is called as temperature. I repeat, all the bodies which are in thermal equilibrium has common property which has the same value for every system. That is, this property is called as temperature. And we can say, if you consider some body, then that is treated in the case of thermodynamics, it is treated as a system here. So if the temperature varies, that is, if the temperature of various bodies, different bodies is different, they are not in thermal equilibrium. It is a point which is clear that if bodies are said to be in thermal equilibrium, then they should attain the same value for temperature. If it is not, then they are not in thermal equilibrium. So the temperature of the body may also be defined as the property by which attains the same value as that of the other body when they are put in contact with the other body for a long time. So this is the concept of temperature. And of course, if you come across the temperature, we should from the lower classes itself, we all know about the concept of heat here. So how heat is defined here is energy in transit here. Energy in transit means energy which is transferring from one point to another point. And of course, we all know the law of conservation of energy, and of course that is also applied for heat energy. And this heat, coming to the heat, the temperature of which is a measure, temperature of a body is a measure of degree of hotness or coldness. So if you consider two cases, say A and B, and if they are placed together, what happens here? After some time, these two bodies can exhibit thermal equilibrium. So something that has been transferred from A to B. So system A and system B, if we consider the two systems, there exists some change of heat from one body to another body. So that's what heat is, a form of energy which is transferred from one body to other body due to temperature difference between these two systems. So that's what heat. So the word heat is only used when there is a transfer of energy between two or more systems. And of course, the third one represents, it means if the flow of heat stops, the word heat can't be used, which is the case of the systems at constant temperature. So if there is no flow of heat, that means the two systems has attained thermal equilibrium in which the temperature remains constant. So if you think of the transfer of heat energy, that means we should know and we should have the word which is coming into your minds, that some work is done, or work is done by the system, or work is done on the system. So if you go for work, if you want to know about work, there should be some force here. So when coming to work, when a force acts on a system such that it produces a displacement in the system, the work is said to be done. Work is said to be done. If that force is exerted by the system as a whole on its surroundings, and a displacement occurs when the work done here is by the system, then of course it is also a work done. So work is done by the system, or work is done on the system. Two aspects are there: work is done by the system, or work is done on the system. So what we can say, there is internal work, and of course there is external work. So is there any equivalence between this heat and work here? Heat key and work, is there any equivalence? That means if you want to know about this heat equivalence, that is we should know the example of a car which is in movement. So if we know that when the car brakes of the brakes of a moving car are applied, the brake, what happens here? uh, what happens here is it becomes hot. That is, brake shoes and drum part becomes hot. When air is pumped into a cycle tire, the pump becomes hot. In all the situations involving which involves the friction value, heat is always produced. So the matchstick is being rubbed becomes hot to burn. For example, if you burn the matchstick on the surface of that particular chemical, then it becomes hot and it burns. So these are the examples which shows that mechanical energy work disappears when heat is produced. This shows that equivalence of work and this heat. So we can observe number of examples in our daily life regarding the equivalence of work and heat. And after that, we should know what is the work which is converted, which is work is done on the system or which is done by the system. Then we should know the concept of internal energy here. So what is internal energy exactly? Here is every system, which every thermodynamic system we say has within itself a definite amount of energy associated with it. For example, if you say a mixture of some hydrogen and oxygen gas on explosion, it produces mechanical energy. As we said in the example, that is, a thermodynamic system has definite amount of energy that is associated with itself. So what we can say, the stored energy which is not apparently shown by a system, which is called as the internal energy, or we can also term it as intrinsic energy here. So, according to kinetic theory of gases, we all know kinetic theory of gases. Of course, the matter is made up of large number of tiny particles and molecules here. So that molecules are not in a constant motion. They can move randomly. They can collide with the other ones, and we can say the total kinetic energy of the molecules, which is called internal kinetic energy here. So this happens due to the collisions which are happening due to intermolecular forces of attraction between the molecules. Then there exists internal potential energy here. So if you have the sum of this internal potential energy and the internal kinetic energy, both will constitute the internal energy of the system here. So this internal energy of the system, which is defined as total energy from all the atoms and molecules contained within your system here. So if you observe this figure, what we can say, internal energy is just not only due to the movement of the particle, but just due to the rest of the particles, of course. So with the help of internal energy, we can predict work is done on the system or work is done by the system. And because of this concept, and we can have this next laws, that is thermodynamic laws, that is first law of thermodynamics. So if you know the concept of heat, internal energy and work done by the system or done on the system, then we can easily express the first law of thermodynamics here. So let us see that. Of course, the first law of thermodynamics, what it says, the energy supplied to the system, that is delta Q, it goes in partly to increase the internal energy, that is delta U, and the rest is work done on the surroundings, that is delta W here. So delta Q supplied to the system, which is used to increase the internal energy of the system, delta U, and that means it changes the internal energy of the system. And of course some part of it is used for external work done. So how could we express it in the equation form? Delta Q is equals to delta delta U plus delta W here. So you can see in this equation here. Right. Yes, delta Q is equals to, we have delta U plus delta W here, and you can easily check that using that system. You can say state 1 to state 2 the system is moving, in which the piston is compressed towards the lower side in the state 2, so that the change in internal energy occurs here, E2 minus E1, which is equals to Q minus W. Heat transfers and it is converted into work done here. So this predicts the first law of thermodynamics. We can observe this first law of thermodynamics in most of the cases around us. So whenever a system changes its states from one state to another state, heat is transferred, so that this heat transferred or heat received by the system is used to increase the internal energy of the system, and of course additional one is used for external work done for the system. So that's what about first law of thermodynamics here. And let us see the other aspects also. What is a thermodynamic process here? We can say thermodynamic process are of many, that is the thermodynamic process may be of quasi-static process, isothermal process, and of course adiabatic process, isobaric process, and isochoric process, cyclic process, etc. And we can deal one by one. And quasi-static process, what we can say about quasi-static process here? So these are the process, quasi-static, isothermal, adiabatic, isochoric, and isobaric, and of course cyclic process. So first one we are dealing with quasi-static process. So what is this quasi-static process? You can see in the figure itself what is a quasi-static process. The figure itself indicates that with increase of volume, the pressure always decreases from higher value. So with increase of volume, the pressure also decreases. So pressure is increasing when the volume is less. That is inversely proportional to each other. So if you observe the second figure here, first in which the compression is more, V1 is the first state, and then last state is V2 here, we can clearly observe somewhat the volume has been expanded. So let us see somewhat the more explanation regarding this quasi-static process here. Yes, we can first know about the quasi-static process here. So, a quasi-state process is obviously a hypothetical construct here. So, in practice, processes that are sufficiently slow and do not involve any acceleration. So these are called as quasi-static process here. So process in which the temperature of the system is kept fixed throughout is called as isothermal. And apart from this isothermal process, quasi-static process is different. So it is convenient to imagine, that is, as because this is a hypothetical concept, it is convenient for us to imagine an ideal process in which at every stage of the system is in equilibrium state. So such a process is in practical infinitely slow. So hence it is termed as quasi-static process here. Quasi-static. The system changes its variables, that is pressure, temperature, and volume so slowly that it remains in thermal mechanical equilibrium with its surroundings throughout its state. And in a quasi-static process, at every stage, the difference in the pressure of this system here is different. That is, everything happens very slowly. So if you take a gas which it exchanges state from pt to another state p dash t dash through quasi-static process, we change the external pressure by a very small amount and allow the system to equalize its pressure with that of the surrounding to continuous the process infinitely, as because it is a very slow process. So that's why the quasi-static process is obviously a hypothetical to construct. So in practical purpose, that is in practice, the process that are sufficiently slow and it do not involve any acceleration, and that's what that is accelerated motion, then this concept is an hypothetical one which is not easy to construct here. So next we are moving on to isothermal process here. So what is isothermal process? We already said that whenever there exists a process, that is a process in which the temperature of uh, the system remains constant here, is that means it is kept constant. It means that is fixed, it is having a fixed value here, and that process is called as isothermal process. Generally what we can say, if you consider a system which is consisting of a gas which is fitted with a piston, then if the expansion of gas takes place by moving the piston upwards, and what happens here, heat transferred from that particular system, and which does not materially affect the temperature of that particular system. So that's what the temperature remains constant. This process is known as isothermal process. And let us also have isothermal process which is in the figure form. That is, here you can observe the figure in which on x-axis we have taken the volume and on y-axis we have taken the pressure here. So on x-axis there exists a volume change, and on y-axis there exists pressure change. That means the system is going from its first state to second state, in which there exist two variables, that is p1 v1 is the first state and the p2 v2 is the second state. So if you observe this figure, what happens here, volume is reducing, and with the volume reduction the pressure is increasing. And p1 v1 is clearly says that at a particular point of v1, p1 is high, and at particular point of v2, p2 is very low here. So the change in these two states will gives rise to the work done here, so that the temperature of the system remains constant. So this is what it is called as isothermal process. So for an isothermal process, what we can say in equation form, we can say PV is equals to constant here. That is, the pressure of a given mass of gas varies inversely as its volume here. So this is nothing but Boyle's law, we all know. And of course if you consider for an ideal gas which goes isothermally, that means at particular temperature from its initial state P1 V1 to this final state P2 V2, at any intermediate stage we can say that delta W work done here is equals to P into delta V here. So as delta V tends to 0, that means when it is reaching 0 value, the quantity delta W over the entire process, then we can say W is equals to integral V1 to V2 P dV here. So we are telling that the system is going from initial state to final state, then we can entirely calculate the work done. W is equals to integral V1 to V2 P dV. So with this isothermal process, we can observe this isothermal process, and of course wherever the temperature remains constant between the two states, then we are moving on to the next process, that is adiabatic process. We all know what is adiabatic process. This process in which the heat remains constant here, that is, there exists no transfer of heat energy from one system to the other system here. So if you want to know whether there exists a change of heat exists or not, then what we should do, whether these two systems are in thermodynamic equilibrium or not. So whenever a thermodynamic system undergo a change in such a way that there exists no exchange of heat between the place or the system and its surroundings, then that is the change is known as adiabatic change, and this phenomena is called as adiabatic process here. So under this adiabatic change, what happens, there is no change in temperature, and of course there is a change in temperature, and there exists no change in heat here. So in this change, heat is developed or lost and can't be given out or taken up from the surroundings. So for example, what we can say, when a gas is compressed suddenly, so we are always considering the example of a cylinder which is fitted with a movable piston, and if it is compressed suddenly, what happens here, sudden compression and exists, and it is allowed to expand slowly. What happens? there is some time gap between this compression and expansion, and if you are doing a compression, sudden compression and rapid um, what we can say rapid expansion, then there is no time available for the exchange of the heat with the system and the surroundings, so that there exists no heat exchange. So if you go for Boyle's law, what happens? PV is equals to constant. So this is what this Boyle's law is not valid or not hold good for the for adiabatic change. So that we should have another equation which represents PV power gamma is equals to constant here. Where gamma we know the ratio of specific heats here Cp by Cv. That is gamma is equals to Cp by Cv. Cp means specific heat at constant pressure and specific heat of the system at constant volume, which is represented by Cv here. So PV power gamma is equals to constant is the equation that represents the adiabatic process. And we also check it over a diagram here. According to first law of thermodynamics, we have Q minus W is equals to delta H here, or else we can say delta U here, minus W is equals to delta H here. So what we have given here is Q is equals to heat input and W is equals to work input and H is enthalpy here. So enthalpy is somewhat developed concept, and if you go on dealing with all the entropy and next and of course we come across in the chemistry also, and in adiabatic process here Q exchange of heat is equals to 0 here. So we are also telling that this enthalpy is a function of pressure and temperature here. We can also say that this absorbed power P is equals to specific work into gas flow, that is G here. So finally what we can say, this adiabatic process, there exists no heat exchange between the system and the surroundings here. So adiabatic relations, what we can say in terms of pressure, volume and temperature for an ideal gas, we can derive with the help of this PV power gamma is equals to constant here. And next we will deal with the isobaric and isochoric process. Yes, coming to isobaric process, we all already know what is an isobaric process. Once again, we are recollecting that what is the isobaric process is the process in which the pressure is kept constant. So the process is represented by a straight line on the PV diagram here. So we all know what is the PV diagram. It is also called as indicator diagram here. So if you take the volume of that particular system, that is a gas on y-axis, on x-axis, and pressure on y-axis, and this diagram, the changes that is happening between the system and the surroundings are represented by using a graph called PV diagram, or it is also called as indicator diagram here. So coming to isobaric process, in this process what is kept constant here? Pressure is kept constant. So a process which is taking place at constant pressure is known as isobaric process. So for example, if you boil some water towards steam, or the freezing point of the water to an ice, an isobaric process, a gas either expands or contracts to maintain this constant pressure here. So if you take the examples of boiling of water to steam or freezing of water to ice, and in which the pressure remains constant here. So how could we express this amount of heat, partly used in increasing the temperature and partly used in doing external work here? So we can say dq is equals to Cp dt plus PdV for isobaric process here. So for example, if you consider the boiling of water to 100 degrees centigrade at atmospheric pressure, then we can represent it by using this equation what is mentioned, dq is equals to Cp dt plus PdV, which is isobaric process here. And if you go for isochoric process, this isochoric process is happening So I think we have crossed that isobaric process, and no problem. This isobaric process is taking place at constant volume here. So wherever this process occurs here is the work done becomes zero here. That is dW is equals to, which is we know the equation dW is equals to PdV, which is equals to zero here. So whenever V remains constant, then there is a change in V, that is dV becomes zero. So that P into 0 becomes 0. So that is the work done is equals to 0. Hence from first law of thermodynamics, what we can say for isochoric process, dQ is equals to only du, because the dW becomes 0 here. So for isochoric process, the volume remains constant, that is there is no change in the volume, that is delta V, or we can say dV is equals to 0, PdV becomes 0, W is equals to 0, and this first law of thermodynamics becomes dQ is equals to only du, the change in internal energy, that is the heat given to the system is only used for increasing the internal energy, or we can say what we can say, nothing external work is done here. And if you come across the cyclic process here, what is a cyclic process here? A thermodynamic process in which a system remains, that is returns to the same condition under which it is started here. So final internal energy is equals to initial internal energy. And again, what is happening here, the particular system, it is coming to its for initial state, final state to initial state itself. So this is what we call it as cyclic process. Whenever a system is taken to its initial state, that is from final state, then in between these two or more processes are happening, and the system or state of the system becomes the initial state of the system. That is when a system is taken from its initial to final state by one or more process, and then back to its initial state by some other one or more process, then that is a function, that is the internal energy of the system becomes zero, because in a cyclic process the initial state is again we are going through, or the initial state occurs after it reaches the final state, so that the internal energy of the system of molecules is here 0, so that delta U becomes 0, and the heat given to the system dQ is only utilized to external work done, not to increase the internal energy of the system. So for a cyclic process, what we can say, this delta Q is equals to 0 plus delta W, so that dQ is equals to, or else delta Q is equals to only delta W. External work is done in case of cyclic process, as the internal energy of the state becomes 0, of the system becomes 0, because the final state, after the final state, and again it goes for first state, that is the initial state, so that the internal energy of the system becomes 0. Again the heat given to the system is utilized for doing the work only, not for increasing the internal energy. So Q net is equals to W net, what we can say in this slide here. And after the process, what we can deal with, we can also have an example of free expansion of gas here. So if you take the special example of this free expansion of gas, it is a best example for adiabatic process here. So what do you mean by this free expansion? So if you consider two vessels which are placed that is, if you consider two vessels which are placed in a particular system which is enclosed with thermal insulation, and of course one vessel contains a gas and the other is evacuated one, and if two vessels are connected by a stop cork, that is the stop cork is fitted between these two systems. Whenever suddenly the stop cork is open, the gas present in the first system rushes into the second vessel, that is evacuated one, and it expands freely. So in this process there exists no time gap, that is no time gap means there exists no exchange of heat between these two vessels, so that this process is considered as adiabatic process, in which dQ is equals to 0 here. Moreover, here we have considered the walls of the vessels are completely rigid, so no external work is performed, dW is equals to 0. So that first, according to first law of thermodynamics, what we can say, the final state internal energy minus initial state internal energy is equals to 0. So that for free expansion of gas, UF is equals to UI. Final internal energy is equals to initial internal energy. So this is what we should have a knowledge regarding this free expansion of gas, which is an example for adiabatic process. Next we are going for heat engines, that is which are based on the number of laws here. So up to now what we have dealt here, a number of laws, zeroth law of thermodynamics and first law of thermodynamics. Depending upon the first law of thermodynamics, we have dealt with the number of process here, thermodynamic process, and after that heat engine, and which was designed for judging the actual engine's performance here. So what we can say, heat engine is a device which is used to convert, or which undergoes a cyclic process here, in which it results conversion of heat into work here. So heat engine is a device in which it is made to undergo cyclic process which results in the conversion of heat into work. So if you observe the figure clearly, there exists Carnot's engine, and in which there exists we have four parts, and first one is working substance, second one is insulating stand, third one is source, and the fourth one is sink here. So what we are doing, we are considering one system here. Well, let me once see you this. Let me give some time. Yes, I have the Carnot's engine diagram here. You can check this because this is a cylinder. You can see here, this is a cylindrical arrangement here, and in which some piston is fitted with it, and then this system undergoes number of process here, and it goes from initial state to final state. And just because of the process, that is exchange of heat between the system and surroundings, and if there exists no heat between the system and surroundings, that's what it is called adiabatic process. System may either undergo adiabatic and isothermal process, either it is adiabatic compression or isothermal compression, isothermal expansion and isothermal compression here. So if you observe, this particular first figure indicates isothermal expansion here, so and the next one is indicating this adiabatic expansion here. So yes, taken here. Yes, the second figure itself indicates what here. This is indicating the adiabatic expansion clearly, and the upward one which indicates the expansion, and the system undergoes first one isothermal expansion to a state, second state, and then it is undergoing adiabatic expansion, and then third one it represents isothermal compression, and fourth one represents adiabatic compression here. And the system is undergoing the cyclic process, as we said, 1 to 2, state 2, and it is for state 3 here, and of course the state 4 here, and again it returns to the state 1 here. So all these process, the either isothermal expansion or adiabatic expansion, everything is displayed, or everything is shown in the graph. Let us see the graph once again. Yes, you can check this. Yes, you can check the graph here. So a PV diagram is indicated over here, in which volume is taken on x-axis and pressure is taken on y-axis here. So here if you observe first state, that is isothermal expansion and adiabatic expansion, it is represented by 1 to 2 here, and of course from 2 to 3 we have another state is there, and of course from 3 to 4 it is exhibiting adiabatic compression here. So all these four states give rise to some work, or may lead to some work. Some of the process may lead to some work, or some of the process may lead to exchange of heat is equals to 0. So how it happens we can see in the second diagram here. So if you check this second one here, TS diagram, with the help of this entropy I came across. With the help of this entropy, if you represent this Carnot's engine performance, then it becomes a rectangle, because the heat remains constant during the adiabatic process, the two process, that is adiabatic expansion or adiabatic compression, and during the isothermal expansion and isothermal compression process, the temperature remains constant here. So if you clearly see this, yes, we have a diagram which is indicated. Likewise, V is taken on x-axis and P is taken on y-axis, and the state of the system during this expansion or compression is represented by points A, which is, yes, this is A, state A, P1, V1, and this is state B, this is P2, V2, and P3, V3, and again here P4, V4. So during this state which is transferring from P1, V1 to P2, V2, we have the work W is equals to here Q1 minus Q2 here. W is equals to Q1 minus Q2. Whenever this working substance is placed on the source, which is a hot body which is maintained at a temperature T1, then the work done W is equals to Q1 minus Q2. And again the working substance is taken out of the particular source and then it is placed on the insulating stand. Whenever an insulating stand is used, there exists no exchange of heat between the insulating stand and that particular what we say working substance. And if you see, the system is going from B to C state during this adiabatic expansion, and what happens, this state only exchanges from P2 V2 to P3 V3 wherever delta Q remains constant, that is delta Q is equals to 0. Q becomes constant, delta Q or dQ is equals to 0 during this adiabatic expansion. And whenever you come across this C, that is C point to D, that is C state, that is P3 V3 2, and again P4 V4. During this working substance is taken and then it is put on the sink, which is a cold body which is maintained at a temperature of T2 here. So if it is maintaining a temperature of T2, that is it is receiving heat from the working substance, which is the system which is containing gas and which is fitted with a cylinder fitted with a piston, movable piston, and this is heat, so that this state that is exchanged from P3 V3 to P4 V4 here. And again the cyclic process goes on, that is from D point to A point, that is P4 V4 to P1 V1. And here itself again we are coming across adiabatic compression. This working substance is removed from the sink and then it is placed on the insulating stand here. So in this way a cyclic process occurs here, we can observe clearly from A state P1 V1 to again it is coming towards the state A at point P, which is P1 V1. So you can clearly check the equations in the next diagram here. Once we will go through it directly, wait for a while. Yes, it is not rubbing, I think. Right. So what we can say, once again we'll go through this diagram perfectly. So this is what is happening at this point, isothermal expansion. From this point to this point, this is adiabatic expansion, and then this is isothermal compression. This is adiabatic, and this is isothermal expansion, and this is adiabatic expansion, and this is isothermal compression here, and of course this is adiabatic compression here. So all these process occurs for different state variables, that is from A, B, C to D, and again it goes to the towards the state A, and that is what we say this is a cyclic process here. So this cyclic process is also having four process, that is two expansions, two compressions. What are those equations? We will see in this next slide here. Yes, if you observe this, already we are told with the first point A, and we come across the point B and C here. For adiabatic expansion, we have the equation P2V2 power gamma is equals to constant here. Just give me a minute. Yes, at point B we can observe the state P2 V2, and at point C we can observe the state V3 V3, which are same adiabatics. If you observe this, we have this equation P2 V2 power gamma is equals to P3 V3 power gamma, which is a constant one. And again, if you consider the 2 points C and D, which are lie on the same isothermal curve, that is P3 V3 power gamma is equals to P4 V4 power gamma, and finally D and A lie on the same, and we can say P3 V3 is equals to P4 V4 here. Whenever you come across this adiabatic expansion, adiabatic process, you consider PV power gamma is equals to constant. For isothermal, you can directly cover this. And if you observe the three equations 2 3 and first one also, by simplifying this we will get log v2 by v1 is equals to log by c v3 by v4 here. So after dividing these equation 4 with equation 2 and simplifying, we will get q2 by q1 is equals to here T2 by T1 here. So the efficiency of the Carnot cycle or Carnot's engine eta is equals to here Q2 by Q1 minus none. And this is this Carnot's engine. We have to know more about Carnot's engine, because this Carnot's engine is, the theory is used to judge the practical engine's performance. So let us see how. Yes, this Carnot's engine, of course, efficiency is calculated by using the formula eta is equals to work done by the engine divided by heat taken from the source here. So how could we calculate? That is eta is equals to W by Q1. We will calculate Q1 minus Q2 by Q1. We all know from isothermal expansion W is equals to Q1 minus Q2, and which is divided with the heat taken from the source. Whenever the working substance is placed on the particular body which is called as source, which is maintained at a temperature of T1, then it receives heat from the source. That is, the working substance receives heat from the source here. So that eta can be calculated by using the formula Q1 minus Q2 by Q1, which is after simplification we will get 1 minus Q2 by Q1. Similar case with the along with the temperatures, we can calculate it eta is equals to 1 minus T2 by T1. So we are calculating the net work done, and we are dividing it with the heat taken from the source here. So if you come across if temperatures is given, we can calculate the efficiency of the heat engine. If heat is there, that is the two values of heat is there, that is Q1 and Q2, then we can calculate the efficiency of the heat engine also. And what is the thing to know about the Carnot's engine is its impracticability. So if practical purpose is there, the Carnot's engine is existing or not. So Carnot's engine is an ideal engine. It can't be realized in actual practice here. So why it is not practicalized, that is why it is can't be practiced in actual case, why we will know. Yes. Yes, in Carnot's engine, heat is to be taken and it should be rejected. That's why again we will go through it. In Carnot's engine, what is happening? The working substance is taking heat from the source and it is rejecting the heat to the sink here. One is hot body and another is cold body. So in practice, in practical purpose, the heat should be taken and is rejected strictly. So in Carnot's engine, heat is to be taken and rejected strictly at constant temperature, which is practically very difficult to achieve. At constant temperature, it is not happening in practical. So in the actual engine, what happens? The temperature of the hot body, which is reducing gradually, and it gives heat, and that of cold body rises as it receives the heat here. So in the practical purpose, the temperature, constant temperature is not it is much difficult to attain that much constant temperature. That's why Carnot's engine, according to the principle of Carnot's engine, the heat is taken and it is rejected to the sink strictly without fail. So it is not possible actually. So that's why there exists impracticability of the Carnot's engine. And of course the base of the cylinder of the engine is assumed to be perfectly conducting and the other parts are perfectly non-conducting, and which is again a feasible one, that is the base of the cylinder of the engine, it should be perfectly conducting and the other parts are perfectly not conducting, and which is not possible in the practical purpose as there exist many changes here, and the engine has very slow working here. It doesn't matter whatever the engine, the efficiency of the engine, and if it is slow working, it may be of no use in our day-to-day life. So I repeat this point because this has much importance, as this engine has very slow working and it doesn't matter whatever the efficiency of the engine it is having, and because of the slow working it is not feasible for us, it is of no use in our day-to-day life here. And finally what we can say, because of this Carnot cycle is a reversible action. When the cycle is reversed, the working substance which is having impracticability action, and so that this Carnot's engine is not realized in actual practice. And of course the actual theory of the Carnot's engine is used for judging the performance of the engines. So this is what I want to deal with today, and what we have dealt here. Once again we recollect what is a thermodynamic introduction and what are thermodynamic variables here: thermodynamic state equation, thermodynamic equilibrium here, number of equilibria, that is thermal equilibrium, mechanical equilibrium and chemical equilibrium. And of course we have a number of process here: thermodynamic process, that is isothermal, adiabatic, isobaric, isochoric and cyclic process. Quasi-static process is there, and of course this heat engine, the concepts of heat, energy, internal energy and work. And after that we have dealt with the heat engine, that is Carnot's engine. And if you come across this Carnot's engine, there exists the reversible and irreversible process. We all know, we observe the reversible and irreversible process everywhere in our surroundings. And if you have any observation regarding this situations, that is if the concepts you have learned in physics, you should see with your perspective that there exists any physical phenomena behind this, what is happening before your eyes. So try to apply the knowledge you have learned, try to put in application, so that you will be having sound knowledge of the subject that you are gaining. And I thank all the that is all the organizing ones for giving such a wonderful opportunity. Thank you all.